Good day, this is Dr. Fredericks again, and I'm here with another video, this time on multiple regression. For this video, I'm going to start off with what you know and build on that to introduce this new topic. Previously, we have looked at situations where one variable is being used to predict another variable. In life, though, there are typically multiple variables that may be helpful in making predictions and better account for more variance in our criterion, also known as the predicted variable. The more variance that can be explained, the more accurate your model or your equation will be at making predictions. Thus, multiple linear regression is an extension of linear regression. Instead of having one predictor variable, we will be looking at two or more. For the purpose of this class, however, we will focus on just the two predictor variable case. Let's think about this. Let's say we had a criterion variable, high school grades, measured by a student's GPA in high school. What factors can we think of that may contribute to high school grades? What are possible predictor variables? So just off the bat, we can think of, let's say, aptitude, study hours, motivation, test anxiety, and I'm sure there are a host of other variables that we can think of that may be good predictors for high school grades. On this slide, we will start with a simple linear regression equation. In this figure, the total variance in high school grades is represented by the blue rectangle. The aptitude will be represented as the green circle within the rectangle. So let's say the relationship between aptitude and high school grades is 0.4. Thus, the percentage of variance in high school grades accounted for by aptitude is 16%. And we know that because that's simply r squared. For simple linear regression, knowing the relationship between x and y automatically allows you to know your standardized regression equation. For the current example, the standardized regression equation will be the predicted z-score of y is equal to 0.4 times the z-score of x. We can interpret beta, or the standardized slope here, to mean that as aptitude increases 1 standard deviation from the mean, high school grades increase by 0.4 standard deviations from the mean. The raw score equation takes a bit more calculation to formulate. However, I have included a hypothetical raw score equation here. And so we can interpret our raw or unstandardized slope, b, here to mean that as aptitude increases 1 unit, high school grades increase by 0.18 units. We can also interpret the y-intercept to mean when aptitude is 0, high school grades will be 0.05. Let's revisit a question I posed earlier now. What other variables do you think will help to explain more of the variance in high school grades in addition to aptitude? So let's say we decided that study hours, the amount of hours on average students spend studying, should help to explain even more of the variability in high school grades. By adding study hours as a second predictor variable, we have transformed this into a multiple regression problem. What makes this more complicated than the linear regression is now we must account for the relationship that exists between our two predictor variables, which in this case is 0.2. Not only do both variables individually or independently have a relationship with high school grades, both are related to one another. Thus, there is variance that each predictor variable accounts for individually, as well as variance accounted for that are shared between the two. And so the Venn diagram on this slide depicts this. Although aptitude accounts for 16% of the variance in high school grades independently, and study hours accounts for 9% of the variance in high school grades independently, of the total 25% of the variance accounted for, 4% is shared. Thus, 12% represents the variance in high school grades uniquely accounted for by aptitude, and 5% represents the variance in high school grades uniquely accounted for by study hours. This Venn diagram helps to simplify the complexities of multiple regression. For multiple regression, the standardized slopes are referred to as beta weights or partial regression coefficients and are often symbolized by the capital form of the Greek letter beta. These slopes will not be the same as the relationships between the predictor and the criterion as it is in linear regression if the predictors are related. In the Cohen text, the relationship between each predictor and the criterion variable is referred to as validities. For example, that would be the relationship between aptitude and high school grades and the relationship between study hours and high school grades. Those would be examples of two validities. Interpreting the standardized slope is a bit different for multiple regression. The standardized slopes here tell us that as aptitude increases by 1 standard deviation, high school grades increase by 0.354 standard deviations, accounting for the effects of study hours. Now, when we say that we are accounting for the effects of study hours in multiple regressions, we are essentially holding study hours constant. We are saying that if all students in the sample studied for the same number of hours, as aptitude increases by 1 standard deviation, high school grades increase by 0.354 standard deviations. Also, as study hours increase by 1 standard deviation, high school grades increase by 0.229 standard deviations, accounting for the effects of aptitude. Therefore, when we interpret a standardized multiple regression equation slope, we're not only saying what happens to y as x increases 1 standard deviation, we have to add that we're accounting for the effect of the other variable if we're talking about 2 predictors. But if we're talking about more than 2 predictors, we're accounting for the effects of the other variables, how many other they are. Additionally, for the multiple regression, because the standardized slopes, regardless of the predictors involved, are all in terms of standard deviations from the mean, these values indicate the unique contribution of each variable to predicting the total variance in the criterion variable. So based on this regression equation and the standardized slopes, we can see that aptitude accounts for more of the variability in high school grades than does study hours, just looking at their standardized slopes here and comparing the two. Clearly, aptitude slope is 0.354, whereas study hours, the slope for study hours is 0.229. The raw score multiple regression equation now looks slightly different from what you have seen previously. Here, B naught is actually the y-intercept. This is what y is when both x values are 0. The raw slopes are calculated slightly differently as well. You use the standardized slope and multiply that by the ratio of the standard deviation of y and the standard deviation of the respective predictor variable to get your raw score slopes. The raw score regression equation is particularly helpful when you want to make specific predictions. The slopes here, as in linear regression, are in the units of the respective predictor variables. Thus, from looking at this equation based on the data in the sample, we can say that when a student has 0 aptitude and has studied for 0 hours, we can expect their high school grade or GPA to be 67.3. Also, As aptitude increases by 1 unit, high school grade increases by 0.28 units, accounting for the effects of study hours. Lastly, as study hours increase by 1 unit, high school grade increases by 0.37 units. Capital R is also called the multiple correlation coefficient, and it essentially measures the relationship between the predictor variables and y. Capital R squared is called the multiple coefficient of determination, and this tells us the total proportion of variance in y accounted for by all predictor variables, or the multiple regression equation. To find the value of capital R, or the multiple correlation coefficient, you take the square root of the sum of the products of the standardized slopes and the respective predictor validities. The multiple correlation coefficient here is 0.458, and this represents the relationship between the predictor variables, which are aptitude and study hours, and the criterion variable, school grades. To find the value of R squared, or capital R squared, you essentially square the multiple correlation coefficient. And the multiple coefficient of determination of 0.21 essentially means here that 21% of the variance in high school grades can be accounted for by both aptitude and study hours. And for the final slide, I have included steps that will be helpful when provided with raw data to assist you in the process of finding both your standardized and raw score multiple regression equations. So here, your first step is going to be to calculate your means and standard deviations for all variables. Following this, you're going to want to calculate all of your validities, or all of the relationships between each of your variables. Third, you're going to then calculate your standardized slopes utilizing the validities, or the relationships between each of your variables. And here's an example of the standardized slope for your first predictor variable. Now, we know that after we've calculated our standardized slopes, we can essentially write, or we then have enough information to be able to identify our standardized multiple regression equation. But if we ultimately want a raw score regression equation, we are going to have to utilize our standardized slopes to calculate our raw slopes. And following that, we can then calculate our y-intercept utilizing our raw slopes to ultimately be able to provide our raw score multiple regression equation. Thank you for watching. I know this was a lot to take in. So if necessary, the great part about having a video is you can always pause and rewind to assist you as you process the information provided. And of course, do not hesitate to look at alternative resources to assist you with being able to process this information. And of course, you have your textbook, which some of the examples, or the majority of these examples, came directly from. So hopefully the video will allow you to read the textbook with more ease and understanding. All right, well, this is Dr. Fredericks, and I am out.